you to Ansys, and then I'll be showing you a demo project. So let's begin. Okay. So, starting off with what is Ansys? Ansys is a computer-aided engineering software suite. It consists of a lot of workbenches that you can use for simulating a variety of different things, from fluids to acoustic waves, that is sound waves, to lights and electrostatic discharge, electrical flows, thermal conductivity, and whatnot. Ansys simulates a lot of things, mechanical structures and all, everything you can simulate using Ansys. So Ansys is used by engineers to simulate and predict how a product will behave in a particular environment or in a particular under a particular external stimulus. So we use Ansys to analyze the product, and if there is a fault, then we optimize it, and and again we test it using Ansys to see how it performs. So, and the best thing about Ansys is that you don't have to actually make a real life prototype model to test it. You could just model it computationally, and then using a variety of different options, you could simulate it computationally, and then it helps you to make the main model. Now, let's say you have designed an aerofoil, you want to test it, but for testing it without Ansys or any other CFD software, you will have to make the in real life, and then using a big wind tunnel, you'll have to test it out, which is very inconvenient. But from Ansys, you can get almost the same results, or you could predict the results without without having to make a wind tunnel or airfoil for that case. Now, in order to understand what is Ansys Fluent, you must first know what is computational fluid dynamics. So CFD, that is what it is abbreviated at, is a branch of fluid mechanics that uses numerical models and analysis along with computational data structures to simulate and analyze fluid flows that help them to predict the behavior and their properties under different temperature, pressure, velocity, density, etc. So it is used in a lot of domains, from aeronautical engineering to automobile engineering to aerospace engineering as well at some points and whatnot. So now coming on to the key highlight, that is Ansys Fluent. So Ansys Fluent is a general purpose CFD software used to model fluid flow, heat and mass transfer, and chemical reactions and much more. So Ansys Fluent is basically a software that uses CFD to simulate all the mentioned systems, that is fluid flow systems, heat and mass transfer systems, and chemical reaction, even microfluid simulation and whatnot. So let us start with a basic idea of how Ansys works. So the first step is pre-processing. In pre-processing, you have to import a geometry, a computerized geometry. It can be in any format. It can be in step format, STL format, or IGES format, or other different formats. And this computerized geometry, you have to either design or either import. You have to make changes. You have to correct the geometry if there are any faults. Now, in this geometry, you perform a very key aspect of CFD simulations, that is meshing or mesh generation. You mesh the geometry. Now, what is meshing? Meshing is the process of dividing complex geometric shape into smaller, manageable elements or cells, creating a grid-like structure for analysis or simulation. So this is required in order to break down the computational geometry into small elements that the computer can analyze and simulate the flow, or in this case flow into. So this is not only used in CFD but is also used in finite element analysis, that is used for structural analysis of different mechanical and structural analysis of different systems. Let's say if you are modeling an aircraft, then if you want to see how structurally stable the wing is, let's say you have to simulate a bird, like a bird strike on the wing, then you use finite element analysis. So this is very important feature of any of a CFD simulation, because it directly affects the precision of the simulation. Now, the quality of the mesh, that is the element shape, there it can be it can be tetrahedral, it can be triangular, it can be octahedral, and it can be quadrilateral. These are the basic four element shapes that are used in the mesh element shape. So these directly affect the accuracy of your simulation, because these directly affect how the computer analyzes your computerized geometry, or how it sees your computerized geometry. Also, the element size. The lesser the element size is, the more finer the mesh is considered. You have to note that there is a limit on how fine a mesh can become because of computational requirements. The more fine the mesh is, the more computationally demanding the simulation is going to be. So it depends from every computer system to every computer system, that how fine of a mesh that you can simulate your flow into. So this is what basically affects the accuracy of your simulation. So in this, as you can see here, this geometry is a computerized geometry, and we perform meshing, and this is how a mesh looks like. Now here are some different types of meshing, like this one, and this one. So it is basically, if you see on this side, it actually represents how different meshing and how much does the uh, element size affects the mesh. So this is a coarse mesh, this is a moderate mesh, and this is a fine mesh. So if you run simulations in these three, this one, the simulation with this one is going to be the most accurate. Now the second step is solving, or the solver, the numerical simulation. So there are a couple of steps involved in here. So firstly, you do a solver setup. So for solver setup, you have to incorporate the solution methods. You have to incorporate the properties of material and the fluid. And then the Ansys Fluent uses the governing fluid equations, that is the Navier-Stokes, the turbulence models, and the boundary conditions to simulate the flow. So what are solution methods? Solution methods, basically there are two types of solution methods. One is steady and one is transient. It affects how the time affects the simulation. Okay, so steady time times the entire simulation at one go, but transient, the time changes with every iteration. It's quite complicated to understand, but yeah, there we won't be digging deep. It's just an introduction. So yeah. Also, you input the number of iterations you want, what is the duration of each iteration, the number of time steps you want, and what is the duration of each time step. So then is the fluid material and properties. So there are a lot of properties of the fluid and material that can be involved in this. For example, viscosity, density, dynamic viscosity, etc. Uh, in Ansys, there is a preset library. You could just choose it from there. You could choose your material and fluid from there, and it automatically incorporates the required properties into the solver. Now, there are some governing fluid equations that are actually used, calculated, or solved by the computer in order to determine the flow of your fluid. One of them is Navier-Stokes equation. So, Navier-Stokes equation helps us calculate the conservation of mass, momentum, and energy in a fluid flow. So the computer solves it. The computer solves it. So this is basically the partial differential equation, and it is solved in every iteration of the solver. And iteration you put like iteration is every time that the solver solves all these equations. The second type of equation that is used are the turbulence models. So there are a lot of turbulence models. Like this is K epsilon, K omega, and LES. So these simulate the turbulence in a flow. Like turbulence is like when chaotic nature appears, so it has to be very complicated. So all these models are derived from a parent model known as the RANS system, Reynolds Average Navier-Stokes system. So we don't go into that. We just use the models as of now. Now, boundary conditions. Boundary conditions are like the inlets, outlets, fluid domain, walls, symmetry planes that you define for the uh, geometry. Now, let's say you want to simulate a flow through a pipe. So, in the computerized format of in the computerized geometry of the pipe, you define the inlet from where the fluid starts flowing, the outlet from where the fluid stops flowing, the walls of the pipe and the fluid domain, that is all the region that is covered by the fluid. Also, in boundary conditions, you enter what are the properties of the inlets and outlets. Now, for example, the velocity of the flow of the fluid flow flowing in the pipe from the inlet is, let's say, 10 meters per second. So I have to put that in. All these models that you see here are, most of them are second degree equations. That means they require two boundary conditions. In this case, inlets and outlets. So you have to define the inlet along with the properties of the inlet, but also you have to define the outlet along with the properties of the outlet. After the solving, there is post processing. In post processing, you see the result of the simulation. So there is velocity and pressure contours that help us understand the fluid behavior, streamlines and vortex shadings that analyze the flow separation and turbulence. So all these are visually represented to us. Also in thermal simulations, we also get the temperature distribution. So this helps us to visually determine what is happening in the system. Also, for some numerical data, as it's mentioned here, lift and drag coefficients. Lift and drag coefficients vary geometry to geometry, and ANSYS helps us calculate them for every specific geometry. So also you could calculate moment coefficient, the what do you call it? Yeah, lift force, the drag force, and the moment force as well. So these are some applications of Ansys Fluent. It is not only used in aeronautical engineering domain, but also used in a lot of domains, even battery simulations, electric motors, rotating machinery, because these all are the domains where something or else is flowing. It's not always about the fluid. It sometimes it's energy also flows. Fluent is able to simulate. For example, electrical motors. The flow of electric charge, Ansys Fluent simulates it. Example, and there are a lot of examples. Microfluid, even it is also used in the biomodeling industry to solve the fluid flow into the aortic geometries for designing better stent grafts or some predicting how the aorta grows with differences of pressure in the arterial environment. Also, these are the application of ANSYS in aeronautics, aircraft design, simulate the airflow over wings and fuselage, rocket and jet engine analysis. There is an entire module of ANSYS CFX known as turbo machinery designing that is used to design and analyze turbo machines. Wind tunnel simulations, yeah. So you don't have to actually have a wind tunnel to run the simulations. Although wind tunnels are considered more accurate than CFD, but CFD is a predictive means of simulating. Also, propeller and turbo machinery, as I mentioned. So, okay, let us try to understand so let us summarize how the ANSYS works using an example of aerofoil. So this is the geometry that I imported. Now I meshed the geometry after creating a fluid domain around it. This is the mesh, as you can see here. These are the more turbulent regions near the airfoils. So these have a finer mesh compared to the boundary regions. These are the post-processing result that contains the pressure contour, as you can see here, the turbulent kinetic energy contour, and the velocity contour. Since this is a 2D simulation, the velocity contour directly represents the velocity streamline. So I have not put the streamlines. So thank you. But now I would like to come on to the most interesting part, that is a project that I took on in ANSYS. So this is the Ansys workbench. As you can see here, there are a lot of different suits that are available in this, but we take that the fluid flow, that is Fluent. So these are the basically 6 steps of Ansys Fluent. Like first is the geometry. In this module, you import the geometry. Now I would like to show you the geometry in Ansys Space Claim. Space Claim is another CAD editing, like computer aided design software of Ansys. So just let it open. Yeah, Ansys is a bit glitchy for your information. Okay, so this is a paper airplane that I have simulated the airflow around. As you can see here, this is the computerized geometry that I inputted into the Ansys solver. So you may ask, why is this? There is an box sort of thing around it. Basically, this is an enclosure. It is replicating a wind tunnel, right? So in for replicating a wind tunnel, this is, you can say, this is a sort of tunnel. The airflow goes through this, that is the inlet, and comes out of this. This is the outlet. So we are taking a section of the air. We are taking the air section when the plane is flowing, something like that. Try to understand. That is why we create an enclosure. Now, coming on to the mesh, I would like to show you the mesh. Now, you have seen the computer geometry. Now, we meshed it for obvious reasons so that the computer can analyze and solve it, solve the equation, governing equations in it. So this is the ANSYS meshing module, and this is the geometry that we imported, and this is the ANSYS mesh. So you cannot actually see the insides of here because every part of the uh, geometry is meshed, but I could show you using the name selection. So this red region is the inlet. This red region is the outlet. These are the walls that we have defined. And this is the airplane that we have run the simulation on. This is the airplane. So the computer is saying, no, the computer is seeing the geometry as like this, the inlet, outlet, walls, and the paper plane. This is what the computer can see, or what the computer can analyze. So now I would like to come on to the setup. Okay, let's go on to the setup. It's quite laggy, but let's just do it anyways. Yeah, it will take a while to, you know, start, but let me try to explain what I can. So yeah, so basically, this is the Ansys UI for Fluent Solver. Just mind the fact that this is Ansys Student, not the actual version. Actual version costs lakh. This is free. So yeah. So also, as you can see here, there is this section for turbo machinery that is able to analyze all the properties related to turbine engines, that is turbo models, turbine performance, and whatever. Also, here you are able to incorporate all the models that you want: acoustics, structure, species. Okay, so basically, you could also run multi-physics simulation with Ansys Fluent. That is the neat part about it. So what this means is that um, this not only allows you to simulate the fluid flow, but also helps you simulate the other things that are being affected by the fluid flow. Now, for example, you are simulating the flow through a garden pipe. Now, you want to see that if we increase the velocity of the flow, how will the walls of the pipe will how will they perform? Like at some point, if the flow speed is very too much, then they will rupture or not. You have to see there. So for that, you need two different parts. You not only need computational fluid dynamics, you also need something known as finite element analysis. Also, let's say you have to simulate something called electroaerodynamic winds or ionic thrust that is governed by the electrical charges and the fluid flows through it. So you can simulate this using multi-physics simulations. So it not only uses fluid mechanics but also a different domain of physics that is affecting the fluid flow or is being affected by the fluid flow. So since this is not opening, I would just close it. I would just show you something else. So yeah. Then is the results. This is Ansys CFD, post CFD module that shows us the results. My laptop is a jet engine right now, but never mind. Now, hopefully this works. Yeah. So this is, as I mentioned, CFD post. So after simulation, after our solver has done its work, after we have incorporated all the factors and all, we get the following simulation results. So this is the same airplane. And as you can see here, these are the streamlines, the velocity streamlines across the paper airplane. Now, these, as this is the vortex generation, as you can see here, the vortex are being formed, velocity vortex, because of the tips. And usually they happen in aircraft as well. There are wingtip, they are known as wingtip vortices. So, wait a second, let me just turn it off. Yeah. Also, it helps you see the wall shear, that is the shear force exerted by the air onto the airplane. So this is a paper airplane. So as you can see here, the regions with the green are facing most of the shear, and these tips of the wings are facing the maximum shear of on the airplane. So this means that if, let's say, you have to make this paper plane, or like, let's say you have to model this more at a bigger scale, then you would try to use much more sturdier materials in this region so that it does not get affected by the shear. Also, I would like to show you the pressure contour. Wait a second, if it works, that is. Yeah, this is a velocity contour. So as you can see here, this is how the velocity is being affected by the fluid flow, by the airplane. So the velocity is high or normal here, and then at the end, because of the drag, it becomes less. Yeah, the velocity of the air, not the plane. So that is how ANSYS post CFD works. If setup would have worked, I would have showed you everything. Let us see if this works. Solution.